This is my third video lesson for the unit measurement. Today we're going to talk about uncertainty in our measurements. Let's go to page 10 in the class packet. Motivation. Do accuracy and precision mean the same thing? So I want you to try to answer this question. So now I want you to watch a TED video. The link to the TED video is in the description under this video. Once you watch the TED video, resume this video. Learning target. At the end of the lesson, I will be able to define uncertainty in measurement and calculate the percent error. Announcements. Homework number 3, it will be based off of this lesson. It will be a junior part. Keep in mind the first exam will be on Unit 1, which was the mattered unit, and Unit 2, which is the measurement unit. So in English, accuracy and precision basically means the same thing in the dictionary. But in science, they have slightly different meanings. Accuracy is how close to the actual reference value, while precision is how close the measured values are to each other. So what does this mean? Accuracy is like telling the truth. Precision is like telling the same story over and over again. Okay? So here are some targets from the textbooks as examples. So basically, if you have high accuracy and high precision, then all your values are hitting the bullseye consistently. If you have high accuracy but low precision, basically you're off by a bit. You're not as consistent, even though all your values are close to the actual value. If you have high precision but low accuracy, you're very consistent in your measurements, but they're not the actual values. And you have low accuracy, low precision, then you're all over the place. So obviously in science and in labs, you want to have high accuracy and high precision, but that's not always the case, right? So the terms accuracy and precision are used to describe the measurements that you have. Okay, so now we're going to do a short reading. I'm going to read to you. Whenever you measure something, you come across a situation below in which there's not enough lines. Therefore, you must estimate the measurements. This is called uncertainty. So basically, when measuring this camera here, you notice that our ruler does not have enough lines. We have to guess, right? It could be 6.5 or 6.6, right? When reading an instrument, you'll read as far as the intervals will allow. Then you will estimate one final place value. This is called the digit of guess and can vary due to it being an estimation. So uncertainty is the situation which involves imperfect or unknown information. So this could be influenced by the instrument, models, operator, or location. Notice with this ruler measuring a nail that the nail is between these two lines, right? So you have to guess the final place value, which causes uncertainty. If you had a better instrument, for example, a better ruler with more lines, you'll get a better measurement. So this contributes to error, which is the difference between the observed value and the actual value. So error does not mean mistake, like someone made a mistake. They don't know how to use a ruler. No, it's based off uncertainty, which is something they cannot control. So basically every measurement will have some error and some uncertainty, right? But you can always try to reduce it, right? That's the goal here, to reduce the amount of error and uncertainty of your measurements, okay? By using better methods and better instruments. So use the percent error equation on table T. So now we are going to do a simulation. Below are 3 rulers, right, with different intervals. I want you to find an object. It could be your phone. Measure the length of the object 3 times using the 3 rulers, okay? I want you to record the measurements over here, okay? Once you're done, resume this video. All right, so here I'm measuring an arrow, okay? So now I'm going to guess the length of this, basically this arrow. So I'm guessing 4 cm, 5 cm. Okay, so let's try the second one. So here we're using the same object, in this case the arrow. Let's guess again. So here we have 4.6, 4.7, 4.8. So notice I have a second digit here, Okay, because there's more lines, I can add another digit at the end. Okay, for the final ruler, now let's measure again. So 4.73, 4.74, 4.75. So again, I have another digit because there's more lines. I can make another digit of guess. Okay, check of understanding. This is important now. Does the intervals or lines account for precision or accuracy? How do you know? So I want you to think about it. Does the lines on the ruler account for precision or accuracy? The answer is precision. Notice with more lines, our measurements are more precise. They're more consistent, right? The reason why it's not accuracy, because the ruler I printed on the packet is fake. If you have a real ruler, you notice that the ruler I put on your packet does not line up, okay? So these rulers are inaccurate, okay? If you have a real ruler, okay? So the lines of an instrument, the intervals, only account for precision, not accuracy. So the more digits you have, the more precise your measurement is, okay? Which instrument will give you a more precise measurement? So here we have an Erlenmeyer flask and a graduated cylinder. Both of these equipment are commonly found in labs. So which one is more precise? So I think you should know, based on what we just discussed, it is the graduated cylinder. It has more lines than the Erlenmeyer flask. Okay, so which instrument will give you a more accurate measurement? It turns out it is the graduate cylinder again. So how do we know this? We will do this in lab. We're going to use a volumetric flask to measure exactly 100 mLs. So when you fill up a volumetric flask with water up to this line exactly, it will give you exactly 100 mLs of water. You're then going to pour it onto each of the container, okay? You're then going to calculate the percent error of each instrument, the graduate cylinder and the flask. Okay? The one with the least percent error will be the most accurate. Okay? So if you do that, it turns out it is the graduate cylinder. So what is a percent error and how do we calculate it? Percent error expresses as a percentage the difference between an approximate or measured value and the exact or known value. It is used in chemistry and other sciences to report the difference between a measure or experimental value and a true or exact value. So the equation is found on table T, so you don't have to memorize it, you just gotta know where to look for it. Okay? So just to check your understanding, does percent error account for accuracy or precision? Since we're calculating the deviation between the measure and the accepted value, it accounts for accuracy. The smaller your error, the more accurate you are. So let's do a Regents free response question. A student calculated the percent by mass of water in a hydrate as 14.2%. A hydrate is a compound that contains water as part of its crystal structure. If the accepted value is 14.7%, the student percent error was what? So we have to use table T. All right, we just plug in these numbers into this equation. Our measure is going to be 14.2 and our accepted is 14.7. You plug this in your calculator, you get this. So assume absolute value, right? Because 14.2 minus 14.7 will give you a negative value. Then you get 3.4%. That's your final answer. Okay, let's do a learning check. The accepted value for the percent by mass of water in a hydrate is 36%. In a laboratory activity, a student determined the percent by mass of water in a hydrate to be 37.8%. What is the percent error for the student measure value? So pause the video, resume once you have the answer. So the answer is 1. Okay, so again, use table T's equation and you'll get this answer. Learning check number 2. A student measured the mass and volume of a piece of aluminum. The measurements are 25.6 grams and 9.1 cubic centimeters. The student calculated density of the aluminum. What is the percent error of the student's calculated density of aluminum? Pause the video and resume once you're done. Notice in this question, they do not tell you the actual density of aluminum. Now, where can we find that information? On table S. Okay, so notice you don't tell you to look at table S. You have to know to look there yourself. Okay, so we got calculated. So density is mass over volume. That'll give you the measure value of that student density of aluminum. Now you look up on table S the actual density of aluminum. You use table T's equation to calculate the percent error, and that should give you 4% error. So this concludes the video lesson for today. Remember to do the Junipod homework.